Did you say rancid?
No, granted.
Granted.
Same time. We're probably going to
Yeah, but that's okay. Like FRQs, they're not easy. Some of them are, but most of them aren't. But that right now, the FRQ is just practice. And I also want to do it about this unit. We just talked about it, so it's fresh. So again, those of you virtual students, the posts you should see, I allowed test correction. So in class, I let them retake their test, copy over the answers they got right to the new test, but then the ones they missed, redo. So I want you guys to do the same thing. I'm going to give you the better score, and whatever your score is, I'm going to add 2 points to it, right? I'm going to give you 10% bumps on all tests to try and help lift our grade up as we're learning this stuff. And then right now, I want to go over the test. I want to review it. What questions you really got stumped on, which ones do you want to see the answers to, and how to do them, to try and clarify, like, that's what I did wrong, right? And then once we talk about all that, then I want to do like a review session, right? I want to keep doing those. I couldn't do it last week. My week was really crazy, so I didn't have time. So I want to do that right now, so we all can take a part of that, since now we have lots of time in this class. We'll do an FRQ from Unit 6, what we just did, simple harmonic motion. I'm going to give you guys time to wrestle through that, just to practice, get an experience of like, hey, this is what FRQs are going to look like. Those free response questions on AP test, we'll slowly keep working at those and build our comfort level with those, so they're not like a shocker when we get to the AP test. You're like, what the heck is this? All right, we'll slowly practice that, and then the rest of the time we can do whatever. So, what questions on the test that we just took do you want me to go over?
Who the ones the dude, the 80 kilogram dude? I missed that one both.
Oh, I don't have this scanned in. Oh yeah, number 9. You're gonna probably kick yourself when you see it. Number 9. This could be a tricky problem, because sometimes they might ask, what's the energy if the pendulum's hanging? Because this problem is a pendulum.
Right.
You got a person sitting on a rope. They're 0.45 meters hanging off the ground. That's how high they're sitting. You don't know the length of the rope, right? But it says, hey, you're pushed until your height is now 0.9 meters off the ground. My question was, what's the total energy of that entire system? Some of you might be tempted, and this is a good thought, because AP might try to do this to you, right? You're hanging, and your dude's sitting right here, and you got 0.45 meters off the ground, right? Then you swing him up here. Now this is 0.9 meters. You understand the problem? Some of you might say, like, oh, he increased by 0.45 meters. I'll just do MGH for 0.45 meters. Well, you're right. That's the energy that was increased from here to here, right? Because there's no motion. It's all potential MGH, right? Gravitational potential. Up here, there is also no motion, so it's just MGH. And the increase was 0.45 meters. So you might do, gosh, that's terrible. UG equals MGH, right? And you might do, 80 kilograms? 9.8, and then 0.45. That would be if I asked you what's the increase in energy from its resting position. I wanted to know the absolute total energy of the whole system. What you should do, because this thing's in motion, you lift it up. Right? So the easiest way to do it is say, I got lifted up here. How much energy do I have in total right here? How do I know that? What kind of energy do I have right here? Do I have spring energy? Should be an easy question. Do I have spring energy? No. It's a pendulum. There's no springs. Do I have kinetic energy? Right there. You lift that guy up to right there and then you let him go. At that highest point, do you have kinetic energy? No. What energy do you have? Right? So then you can just say M, G, H. Does that make sense? This one actually was just a, can you apply energy to a pendulum problem? Does that make sense, Ethan?
Why does the, because if he's on a pendulum, why does the energy stay if he's not falling?
He does fall, right? You lift this guy up
Right.
here and then let him go, and he's got simple harmonic motion.
Right, but from the resting position, he's not falling.
Right.
So you lift him, and his energy becomes from the resting position.
Right, but he's already got potential energy here. So I was basically asking, this potential energy plus this increase in potential energy adds up to how much does it have in total? Does that make sense?
So then where does the rest of the energy go?
The rest of...
If you have to... If all of the energy stays, where does the rest of the energy? Because it turns into kinetic energy.
Yep, and then you get
potential.
here, and you have a bunch of kinetic energy and still a little bit of potential.
See, oh, okay, I got you.
Yeah,
Okay.
that was my... The question was, like, what is the total amount of energy that the system has? So I wanted to know, like, right here, you realize, like, nothing's happening. It's just off the ground a certain distance. That's all the energy there. I can calculate that. It was, what, like 705.6 joules, I think.
So when we were calculating for the energy of the pendulum, we weren't taking into account for the distance off of the ground.
Yeah, did you guys just do this? MGH?
I just did H's from its resting position. I took that as 0.
Oh.
That's the way we had done it before. Was in, all of it was in kinetic energy.
Yes. However, this question, you don't start at 0 meters. Right? Your 0 point isn't here. Your 0 point's here. That's why I was saying, hey, this pendulum initially starts 0.45 off the ground. Then it increases more. Right? What was the energy at that point? So the energy, it has this much energy. Halfway, when it gets that back to the bottom, in this case, half of the energy is lost and switched into kinetic energy. The second half is still potential because there's still a height difference off the ground. Right? So this was, I didn't mean it to be tricky, but that's why I was saying, like, hey, that total. I was highlighting that total energy. What is the absolute total energy? Well, you say, like, okay, at this point, nothing's happening except potential. I know the formula for potential. It's a good question to talk about because on the AP test, that they might throw in a little quick blurb that says, like, an equilibrium position, or how could they phrase that? They could just be tricky with their wording and basically tell you, like, use this as your equilibrium position. How much energy does this system have? Well, then you would be like, well, this is my 0 point. This is 0 energy of any way, shape, or form. I increase it here. Well, I lift it off the ground. I added potential. How much? 0.45.
Right.
So my system is 0.45. Goes all to kinetic, and there's now no potential, right?
Okay, yeah.
So, if anything, use this to, like, remember, AP, be very careful you read the question, because sometimes they'll ask this question, but they'll have you use this as your equilibrium point. Other times they're saying, what's the absolute total? Well, in that sense, ground is always your 0 point, and everything goes off of that. So I didn't mean to trick you on that question. But that's why I was in class. I was like, hey, this total, like, it is the absolute total. Do what you normally do. Okay? Any other ones that I can go over quick?
The one that was like worth 4 points.
Worth 4 points? Okay. This one, right? Okay, so this one wasn't meant to be hard. I told you that too. I told you this one is not meant to be hard. There is some tediousness to it. The question, you got 4 situations. They're a different spring constant, a different mass, and a different stretch. You're told to rank the period, which is T, the time for one oscillation. The big thing, basically what you need to do is for each one, the period for A is 2 pi root m over k, straight from your equation sheet. What was the mass of this? Well, it was 1. What was k? It was 5. You're like, okay, that's something. Now for B, 2 pi root mass was 2, k was 5. Which one of these has a larger period? Right? This number is the same. This is square root of 1/5, square root of 2/5. Yeah. The square root of 2/5 is bigger. Right? Let me, just so I don't drive myself crazy, let me confirm that. Yeah. The square root of 2/5 is 0.63. Square root of 1/5 is 0.45. That's all you had to do, and you didn't even need to do the math, right? The 2 pi will be the same in every single one. So Cu is 2 pi. 1 kilogram, 1, so 1 over 1, was the mass divided by the K. D, 2 pi again, root 4 over 4. And then basically you could say, like, compare all these numbers, right? 2 pi times root 1/5 is smaller than 2 pi times the root of 2/5. So in this case, B, and you got to rank them greatest to least. So B is bigger than A. Right? Then you're like, okay, what about this one? Well, this is the square root of 1. Square root of 1 is bigger than the square root of 1/5. So C, and it's bigger than the square root of 2/5, so C is out here. How does C and D compare? They're the same. 4 over 4 is the same as 1 over 1. These two are exactly the same. So C equals D. This option. C equals D. This is bigger than both of these. This one is bigger than that one. So that's the order. Equal, smaller, smallest. Aiden?
You got that wrong. I guess that's the first
No, that it's graded automatically. And yeah, this option, C equals D, greater than B, greater than A, would be counted correct. It shouldn't have made a mistake. Because these are graded automatically. If you chose that option, you got a point. Alright? Does that make sense? So that was my warning. I was like, hey, this looks long and tricky.
Pick the other one. Pick the other one that's equal.
Yeah.
I made the same mistake.
So this one was basically doing this and then comparing them. Now, you've done this lots of times. It's your basic period for a spring. Does that make sense? Okay, any other ones? I will talk about this one. This one, you're given a mass, a graph of velocity time, and you're asked to find the spring constant. Right? So some of you are like, well, I didn't know where the heck to start. I know for a spring block system, I got this equation. Right? So you're like, wait, I got a mass. That was given to me in the problem. I need to find K. You'd be like, well, crap, can I get this somewhere? If I can, I'll just plug it in and solve for the unknown. Can you find the period from this graph? Yes. Remember, simple harmonic motion, it's repetitive. Right? That spring goes back and forth. Right? The acceleration at every point, it goes through a cycle. The acceleration comes back to what it was originally after a period. So in this case, the velocity is cyclical. Right? I have a ton of velocity that happens right in the middle of my motion. Right? When it passes that equilibrium point, it's going the fastest. Then it slows down and stops at the end. Comes back the opposite direction, has max speed in the middle, but it slows down again until it gets to the other end. And it stops momentarily, then it picks up speed and comes back, and now it's completed a full cycle. So you could look at the graph and say, hey, from 0 to 3 seconds, that was where one cycle went down and came back. And it goes down and comes back. Well, this is my period. Right? Plug this in here and solve for K. That was what that problem was going to be. Pulling a piece of information from a graph and then plugging it to an equation we've seen and used a lot. The 2-question answer, what was the answer? What were the 2 pieces of equipment that we needed to use?
Balance scale.
Wait, what? Balance scale? Yep. And a stopwatch. Why do I need a stopwatch? Well, first of all, I need to know the spring constant. Again, you can be like, well, the one equation that I know I got is this guy. I need this. Well, if I'm going to take measurements, what 2 variables do I have left? I got the period and the mass. That if I know those 2, I can solve for this missing value. How do you measure the period of something? What piece of equipment do you use? The time it takes for one oscillation. The stopwatch. Right? You can let it go, start the watch, and stop it when it gets back to where it started. So stopwatch is one of the answers to get this piece of information. Then, to get the mass, a scale. Right? Put the block on a scale and see how many grams it is, or kilograms. Those are the 2 answers for that one. And then the longest one, this was straight from the AP, I think the multiple choice. This one was probably the hardest because you have to find the displacement, right? The maximum displacement is given here, right? It goes back and forth equally around this point, right? So what's the max displacement? Well, it only ever goes up by 1 or a half or down by a half. So the max displacement from the midpoint is 0.5. Once I know x, then I go to energy, right? And you're like, hey, I got this. I need this. I don't know K. You're like, well, crap, I gotta find K somehow. How do I find K? I got the mass. I don't know K. Can I find the period? Yeah. Pretty much any graph of simple harmonic motion, you're like, hey, it starts here, comes back after 3 seconds. I know this. I solve for K. K equals, I know it. Plug it back in here. Then I can solve for the energy, which is actually what the question asks. It's another AP question where it's multiple steps. They're going to give you a bunch of info and ask you for something, and you can't just plug it into an equation and calculate it. You probably have to use maybe 2 or 3 to kind of follow the chain to get there. That was the tricky one because it was multiple parts, like multiple steps to get to what you want. Any other questions that I can answer? Any of them I can clarify? Help explain like why you were thinking about it wrong or something?
What was the other one? The graph?
This one?
Yeah.
Yeah, so that was the one we had just talked about. You basically find the period, right? It repeats every 3 seconds. So the period is 3 seconds. I'm trying to find K. Well, if it's a spring block system, I got an equation for the period. T equals 2 pi root m over K. I got this from the graph. My mass was given to me in the question, 1.8 kilogram. I only have one unknown, so plug in the 2 things and solve for the one missing variable. And you would get 7.9. Feeling good about that? Okay, so I want to then shift gears to the FRQ. You can do this either way. I want you all just get a piece of paper out, right? This isn't graded. This is just a practice for us, right? If you want to look at this on your own, this is assigned in my AP classroom. You can view it. I'm going to try and show you step by step here. So we're not going to do the long one. We're going to do FRQ number 2, which is the shorter one. Alright, so y'all see this. I want to give us like, what's a reasonable time? Let's do, want to try like 8 minutes to start? Yeah, Mr. H, that sounds good. So right now I'm going to try and scroll through this. If you want to look at this on your own and go back and forth, this is assigned on my AP classroom. We're just doing number 2 right now. This is not graded. It's just your practice for the AP test. It's a free response question. So you got this graph. I'm going to try and get you started on reading through. So spring potential energy versus position. Right? This is its equilibrium point. If you pull it back, it builds energy. Right? When it comes forward, it loses all the energy and then builds it back up. Which makes sense. As it oscillates, as it gets away from the midpoint, it builds energy. You got, it's the mass, 0.4 kilograms, it's horizontal. You ignore the mass of the spring. Right? The spring is attached to the wall and the other end is on the block. There's no friction. You take the block and you stretch it 0.25 meters beyond the equilibrium position and release it. So you pull it out all the way out here and then let it go. This is the graph of potential energy as a function of where the horizontal position away from equilibrium. Positive direction is considered to be to the right. So positive 0.25 meters means I take the block and I pull it to the right, well, for you guys, to the right, 0.25 meters, and you let it go. It's asking you, sketch a graph of the force exerted on the spring, or exerted by the spring on the block as a function of position. So this is one where you're going to have to figure out, how do I find this force on a spring? How do I get that number or information to find that number from the first graph that they gave? So that's part one. Draw the force as a function of position that acts on the block. Then calculate the period. Right? All of you should be going to your equation sheet and being like, hey, period of a spring mass system is 2 pi root m over k. This was given in the question, right? This I got to find out to find the period. Plug that in for B. Actually, another question. Do you want me to stop talking for a sec to work on part A and B? Or do you want me to keep reading the options? Yeah, and again, I'm trying to show it up here, but I can't scroll and show you exactly what you want to see as you kind of go back and forth. Give me the force, calculate the period. Then you got, hey, a new mass. You've increased the mass. You do the same thing, same distance. Now tell me, it shows the kinetic energy. Or actually, it asks you to find the kinetic energy. The key here, it's the same spring. It just has a different mass. So that's ABC. Part A is show me the force as a function of position. Then find the period of oscillation. Then C is show me the kinetic energy as a function of the position, the location, with a new mass. Is there something I can show up here? Want me to show this for now? Just yell at me and tell me what to move to if you're looking at the screen. If you've got it on your computer, you can scroll and look at whatever part you want. Got like a minute left. Again, I'm just estimating approximately the time that you would want to spend on this problem before moving on to the rest of the problems. Oh my, that's extremely loud. Okay, so now I want to pause wherever you're at. Hopefully you got through a majority of it. What I want to try and do is I want you guys to tell me how, if you figured these out, how you did it. I want you to collectively tell me how to solve it. I'm going to pretend that I can only do what you tell me. So I want you to tell me, how do you figure this out? Did someone get the first question? Or have an idea?
You will only do what we tell you.
You know what I mean, though. Right? We're trying to sketch the force that the spring applies on the block as a function of position.
How are we supposed to sketch a graph when all of us do is type in the box?
You'd take the test pen and paper and draw this. Yeah, you would draw the graph. The box is, you could have you could explain what you did. But on your piece of paper, you would draw on this graph. Can anybody tell me what would the force on the block be right here in the middle? I heard it. You got to think of these checkpoints, right? Okay, the very middle of the motion. This 0 represents 0 displacement from a rest position, an equilibrium position. My spring's right here at an equilibrium position. Is the spring applying any force? No. You could draw a dot, like, hey, I know at that point in time, there's no force applied on the block. Does anybody know what equation we're going to need for the force of that spring? That'd be a really important thing to know to do this problem.
It's Hooke's law, right?
Hooke's law. Force of a spring is what? Kx. Negative kx in particular. This gets tricky, but the spring acts in the opposite direction of the displacement. If I pull it to the left, the spring's going to pull to the right. It opposes your motion. So, do a checkpoint. What happens all the way at, let's go right out here, all the way at 0.25 meters. The maximum distance to the right. What's the force? Yeah, we got a problem, don't we? We know the distance, but we don't know K.
You can find K with using potential energy.
Yes, right? Pick this point. Potential energy of a spring is 1/2 kx squared.
We know everything there.
Yes, except for K, which we want. Yep. So, right, you're looking at this graph. It literally tells you energy. What is that? 10?
10.
So 10 joules of energy, 1/2 K we don't know. What's the displacement at that point? Whoops. 0.25. squared. This is algebra. Solve for K. Did anyone get it? Of course, I just put my calculator away. So 0.25 to the second times 0.5 and then 10 divided by that number. K is 320. 320 newtons per meter. Now I can go over here and get my force, which is actually what I want. 320 times 0.25, it's negative 80 newtons. I'm finding a force. So I'd go to my graph and I'd say, hey, at the very end, I would do something like 20, 40, 60, 80. 0.25, I had 80. 80, 60, 40, 20. Right? So you got a checkpoint there. Okay? Now, you just got to get some more data points to look at. Is this a line? Is it a curve? Does it curve down? Does it curve up? Now, some of you should know this, but you can confirm by like, okay, do something in the middle. Let's do 0.1. If I do negative 320, 0.1, what does that give me?
32.
32. Oops, I already made a mistake. Did I get 80? I got negative 80. I got to put it down here. Again, that'd be a really subtle thing, but that would be the difference between getting this correct and incorrect. Negative 32 at 0.1. 20, 40, 60, 80, 32, something like right there. Does that look like it's going to be a line or a curve?
That's pretty straight.
Looking pretty straight, right? Now you can do this, but you could also be like, huh, the equation is a line. As I increase this, this goes up. It's linear. It's a one-to-one thing. There's my line. Now you got to just quick check, okay, what about the other side? Again, you know this, or you can know it, right?
It's the same thing, just positive.
But, yeah, what if I put in a negative 0.25?
Same thing.
You're going to get the same thing, but it's going to be a positive. You're going to do this. You can quickly see it's a straight line. That is your force plot as a function of position. The trick is you don't know K. You're like, oh crap, where do I get it from? Got to use that first graph they gave me. Then I can just do this. Hooke's law, take a position, plug it in, find it, plot it. Do it a couple more times to get the shape, and then draw that in. Okay, so that was the A. B, period. You should be like, hey, period is 2 pi m over k. We know both of them, right? What was the mass? 0.4. So 2 pi, 0.4, 320. Plug and chug. Square root of 0.4 divided by 320 times 2 times pi. 0.222. Seconds. That's part B. Quick math, plug it in. C, you got kinetic energy. Or you're trying to sketch the curve for the kinetic energy. Well, this one,
Isn't it exactly the opposite?
huh?
Isn't it just exactly the opposite?
Opposite of what?
The potential.
Yes. Did everybody catch that? Ethan caught the trick that would help you do this quickly. He's like, hey, wouldn't the kinetic energy at any position be the opposite of the potential energy at any position? And you can check yourself, right? At the very, very middle, there is no potential energy, right? The spring isn't stretched or compressed at all. If there's no potential energy, where is all the energy in the system? It's kinetic.
See, this is where I got wrong on the last problem.
Okay.
I found out that 1 kilogram, 80 kilogram guy problem.
Yeah. It's hard. You got to define your system. What's the maximum possible energy?
10.
10. So you know, hey, when there's zero potential, the energy has to be somewhere. It's a conserved system. So I'm going to plot here. At this, I have all of the energy is kinetic energy. So there's my kinetic energy. Right? Give yourself another checkpoint at the end. When you have all of your energy's potential, there's no kinetic left. So you got 0. If you realize the potential and kinetic have to be opposites, your graph is just flipped. Okay, so again, sorry we didn't have time. It always takes longer than I think to explain. Hopefully that helped. Again, boost your grade and test scores. Help clarify some things. Good practice for the AP test. Get a little exposure. Next class, we'll start our next unit. We'll start introducing torque and rotational motion. It'll be our last unit, which is kind of crazy. It'll be about 3 weeks. About 3 weeks for this unit. Probably a little bit longer. Then we'll be done, and then we'll just be full-blown review mode. All right? So we're doing okay? You want those points for that question? Did you get it right and you chose the wrong option?